Hi, everybody. Welcome to week 9 of the summer term. It is August 19th, 2021. We are hoping to wrap up our project within the next 2 weeks. And in order to do that, there's some things we should talk about. So first off, let's look at the progress of the paper. So everything in black is what was written as of last week. Before last meeting. Everything in blue is what I've added since then. Purple are corrections I've made to other people's work, and then red is what I think we still need to add. So for instance, I found this nice paper that actually does time series sparse coding, and I think that this would be a good reference. So I want to add it to the sparse coding background section. I'll be bugging people in the chat to see if anybody can help me out with that. And then when we talk about the network architecture, we're dealing with 2 networks here. We're dealing with a sparse model that Isamu created using the ISTA algorithm. So he created, I can show you. He created some layers, like an activity layer, a dictionary layer, and then he's using that he extended the Keras models class to create a model that would, do the ISTA algorithm. I don't know much about ISTA, so he sent me a pretty informative YouTube video tutorial. So if no one else wants to take care of that section, I'll research and add some information about that. Aside from that, we don't really have any figures. I mean, this table shows what the LSTM looks like. I still have to fill in the parameters. It's relatively simple. We're using 64,000 units to predict, 6,400 units to predict the next 128. I wanted to add this figure. This kind of displays the data we're working with. So on the left-hand side, we're dealing with 1,000 hertz signal, where we have n samples, and the features are the 6,400 points, and then the ones we're trying to predict is the next 128 data points. And then I drew up this figure to kind of explain the algorithm. Basically, the way that I intended it to be interpreted is you have L generations. So of the genetic algorithm, you have L generations, and then for each generation, you have K children. And in the first generation here, each child starts without a prior to the weights. So the weights are initialized randomly for the LSTM model. For each X of T in the first generation, we are predicting Y prime of T, and we're using ISTA to form a dictionary and activity matrix from all of the features in the first generation. And then we're using the reconstruction loss between the dictionary activity and the predicted target values to determine the best weights associated with each child in the first generation. And then those weights are what used to kickstart the next generation. And then through the training process in the next generation, the prior, I used lowercase and uppercase gamma, but the prior is free to be optimized through the training process. So that's kind of what I intended for it to be interpreted as, and I might make I'll probably make many changes to it before I write a caption and insert it into the figure. But these are the 2 main figures that I have for the paper. Are there any questions or suggestions? I did that without any. This is the first time I'm explaining it, so hopefully it makes sense. It might be a little compact or too cluttered, but Ansh, what do you think?
Yeah, I feel it's pretty discrete and gives a holistic view of everything what's happening
Okay.
in the algorithm. I
Yeah,
guess it's pretty cool.
I think it's cool. So yeah, the algorithm is cool. And I ran the algorithm over the weekend. It took a long time, and I did it without with pretty when you think about how many parameters you might have. I did it with a relatively low number, not of parameters, but I set the parameters to a low setting so it wouldn't take forever and it wouldn't kill my MacBook Air. Um, for instance, the LSTM model is relatively simple. Um, I don't know how to beef up LSTMs without, increasing the dimensionality to a point where it can't even run on my MacBook because it runs out of memory. That's happened to me many, many times. Um, but I'm assuming that it'll perform much better if the LSTM model is a little beefed up with some either more layers or a variety of activations. Um, and if we actually use more samples, I used I think 5,000 data samples from 50 patients. In the data set we're using, there are just 50 patients, and then I just extracted 100 samples per patient. And those are the segments I used here. So when you look at the results, for instance, I have the results on a per generation basis. So this is the last generation. And sorry, this is the last fold. So we did 10-fold cross validation, and I was looking at how the weights, how the LSTM model performs given the last weight in generation 9 versus the original weights in generation 0. So we'd hope that the R2 is higher um, for the newer weights, and the RSME is lower for the new weights. But you can see that the numbers are relatively the same, at least for this fold. Which tells us a couple of things. It either tells us that our optimization function isn't optimizing as much as we'd like it to, or we have relatively few parameters for which we can optimize. So if we look at just some of the other ones, yeah, like this one, the values are really close together. What I would consider negligible improvement, if any, up here for this generation, pretty much the same. But I don't attribute this to the algorithm's fault. I kind of attribute it to um, the uh, the lack of parameters we have, or the simplistic nature of the LSTM model. I think that's a bottleneck because, Alicia, in the first one you proposed, you had 4 6 layers in the what was it, predict forecast function, and
Yeah.
I got rid of that because it would have taken forever to run on my computer.
Mm-hmm.
Um, so I'm gonna try to see if we can spin off. I'm gonna see if we can investigate, what this means in regards to the performance. Didn't necessarily. It probably didn't significantly improve the predictions, but I wonder how much of that is due to the fact that we're dealing with a pretty simple prediction model, and we have relatively few samples. I mean, we're looking at 5,000 samples, and then we're doing 10-fold cross validation. So each one is only being trained on 450. We're splitting it up into 10 folds, where 90% is test and 10% is where 90% is train and 10% is test. I think that's how I split it up. So you're training on 450 samples, which isn't ideal. And, there's another thing too. Because of the ISTA algorithm, you have to kind of pick the dictionary size. The dictionary size has to be divisible by the number of features you have. And so my original idea was to compare the, I'm going to compare like the predicted signal. If this is the predicted signal by the LSTM model, I wanted to compare that to a dictionary. So this is 128 points. I wanted to compare this to a dictionary that's relatively, small, right? So I was expecting the dictionary to be maybe like 32. I'm using squares here just to illustrate it, but like a singular dictionary element or singular atom in the dictionary would have 32 points. But because of some constraints with the ICA implementation, I actually changed the dictionary size to 128. And the reason why this is a little problematic is because you're assuming that your prediction will show up in the dictionary instead of, assuming that you're assuming that, the best case scenario is that this is showing up in the dictionary. You might have something you might have some dictionary element that, isn't quite like it. Maybe it's like a little switched down version of it, but you can throw some coefficient on it to make it that. But I think that the reconstruction error that was calculated here was greatly inhibited by the fact that we weren't dealing with smaller dictionary elements. We were dealing with dictionary elements of the same size of what we were trying to predict. But last time that Yit and I explored time series prediction, our objective function just didn't work. I think that there is, some things we can say about this. I mean, the average number of epochs for the loss to stop converging did decrease as you from the first generation onward, which indicates that the weights that you sent to the next generation were a good prior. Now, I don't know if that's because those weights were the best weight for a given generation, or if those weights were, picked out from just those weights were the reason why those weights worked is because they were found because of like back propagation, and that was the reasoning. There are a lot of different ways we can try to spin this. I'm sorry, I paused my screen. What we can do is we can actually we can wait until we send this algorithm to a more powerful computer that isn't mine and see how it performs when we increase, the dimensionality. So we use a more granular dictionary of 32 units like I originally wanted us to. And then we use a larger LSTM, one that I wouldn't know how to make it right now, but I don't know what's ideal for this, but yeah. But the thing is we don't have to, have results right away. I think in these past weeks, we've worked on developing this algorithm, which in my opinion should work, because you're basically trying to find the best prior for the next generation using the reconstruction loss of a learned sparse dictionary compared to the predictions of the LSTM model. And the idea is that you find the best, you're going to find the best lowercase gamma here that minimizes this reconstruction loss per each generation, and it should just get better and better. But that might be at a fault of the hyperparameters we chose. Yeah, right now it's 128, which isn't ideal because that's the length of the YFT we're trying to predict. Yeah, I'm actually getting an Intel Nuke on Thursday, which is a really small computer, and I might run this on there, but with those changed hyperparameters to see if the algorithm improves or by how much it improves. Some things I did during the training process is I saved the sparse reconstruction. So if I want to run it again, I don't have to waste time on, you know, sorry, these are the saved dictionaries. I don't have to waste time reconstructing or running the LSTM model. I also save the results. So if I wanted to, I could simply have these results on hand after each generation per each fold. So if we have 10 folds and 10 generations, that's 100 data points for R2 and the RS root mean squared error. Yeah. So does anybody have any suggestions for next steps other than what I mentioned? It might be that I'm, overlooking something.
I was just curious if you looked into using a GRU instead of LSTM, because at least that one is like a simpler model.
A GRE?
A GRU.
A GRU.
Gated recurrent unit.
I've never heard of that before, actually.
It's,
Could you send me something that,
yeah.
Now, what is a GRU? Figure this out. Gated recurrent unit. Okay. It'd be interesting to compare, like if a GRU performs significantly better than an LSTM. I don't know what that says about the algorithm, that it being sensitive to, the differences between the two, but that's a good suggestion. We could actually add that into our comparison. Are there any other models that besides LSTM, or I mean, we could just use like a recurrent neural network as well, right? We wanted to survey.
Yeah, there's a lot of different options. I was just saying a GRU tends to be simpler than LSTM and
Okay.
requires fewer parameters. So in the sense of
okay. Is what's the Python implementation for that? Is there a framework? Can you do that in Keras?
yeah, you can actually really easily substitute a GRU for LSTM in Keras.
Okay.
Just like kind of spot the layers and reduce
Yeah.
the amount of states you're passing along.
Yeah. Thank you.
Yeah.
We'll look at. I'll look at that. And from a sparse coding point of view, do you think there's a disadvantage to having a dictionary? Like the idea is we're trying to evaluate how well the predicted values of Y match the dictionary that we learned from the training set. And then we're using the argument of the reconstruction loss to pick a prior for the next generation in the genetic algorithm. You think there's a significant disadvantage to using like a dictionary that's as large as what you're trying to predict?
I mean, yeah, you could definitely say that could be a disadvantage. Have you tried? I didn't look that much, but if you like have like a 64 dictionary.
Yeah, I want to try. I want to try 64, 32. Asamu told me to make it 128, but I think that's an oversight to do that, because I think you're not gonna have as much information. We ran in. I think the reason why he said that as a simple fix is because we ran into some like reshaping errors when it came to like reshaping the data. But I think I understand what everything needs to be divisible by in order to properly implement it. Yeah.
It's definitely, you could, if you did like 128 and then 64 and compared the results, even on like a smaller depot count or something, you could see if it gives favorable results.
Yeah, that's true. That's true. Do you think that, and we're doing the tenfold cross validation here. Do you think that 500 samples is too few per fold to do, because you're using that for generating, so it's 500 by 6400, and you're generating the dictionary, and then you're using those 500 for LSTM predictions as well. I could increase it up another magnitude, up to 50,000 total.
I mean, yeah, that would definitely probably work better the more data you added, but I think 500 seems sufficient.
Okay. It's also my computer would die, I think. So cool. I'll look into that. And would there be any other figures people suggest to add to the paper besides, we want to show the data A, we want to show the algorithm B. I don't know if there's much else. I don't know how often they have figures in future work, but it'd be cool to just have a figure dedicated to the amount of data sources to which this algorithm would apply to. For instance, like we're applying it to ECG, but there might be some stretch of EEG to which you might apply this to, or the waveform for different physiological measurements like ICP. That has a very distinct waveform that ends up repeating. Intracranial pressure is the pressure below the cranium, and it tends to have this 3-peaked pattern that repeats itself like this. So it's a period. It's kind of periodic, except it's not. There's variations in the mean of this if you want to call it a period, the thing that tends to repeat itself. It's like how this is kind of periodic, but not, because there's noise associated with each beat. It would be cool to show.
So we can show like similar to what Osamu did with the prediction, right? And then what was the actual result of it? Similar to the number, right? And then what was predicted, the sparse coding versus what was the actual result.
Yeah, you mean like comparing to a baseline?
Yeah.
Yeah, so the way I did that, or thought to do that, is just comparing the first generation to the last generation. And what that does is basically the first generation for the original weights would be something that isn't are the LSTM models whose weights aren't selected based off of the this optimization, and then the new weights are the ones that are selected. So those would be from the last generation. But do you mean like displaying that in a on a figure? I think that'd be interesting, because like these, what would be really interesting is if the R2 and RSME are close together, but then there's an obvious difference when you look at the data, right? If for some reason the RMSE is the same, but one is visually more accurate than the other. I think that'd be interesting. And that's something I didn't think about.
Yeah, but how would we show it?
Oh,
Again.
just like this, you have one color is the old weights, the next color is the new weights, and then the other color is what the signal actually is.
Got it. Okay.
Yeah, something very similar to like this. So yeah, so that's some more work to do. Probably dedicate maybe Thursday morning to doing that. Ooh. And then from a paper point of view, I mentioned this in the background, and then if we are going to incorporate GRUs with LSTM or one over the other, we're going to have to incorporate that into the introduction and then the background as well. And then I'll have to research ISTA, and then that should be it. We're just missing the bulk of the results in section 4. And the thing I've noticed with these sort of papers or papers that are more exploratory in nature for like algorithms is that the performance doesn't exactly matter. We had a paper fall term, I'll pull it up, whose results were kind of questionable, but it's been accepted to a bunch of conferences. We looked at binary search as it applies to neural network optimization. I came up with this algorithm too, and it works when you assume a distribution, when you assume like looking at a metric, but we're looking at accuracy here. You assume a distribution of how that accuracy varies with a parameter like the number of human units, and you can use the gradient of this distribution to find the maximum accuracy. I think we formalized it somewhere like here. And when we applied it to actual data sets, it worked pretty well. There's some instances where it didn't. Even then, we were using some assumptions to find this. Like, we do a bunch of data, and then we do a bunch of training at different hidden unit sizes, and we would search on the polynomial that fit that. So we wouldn't fit on the individual data points, we'd fit on the polynomial. So there were still a bunch of assumptions with this, and maybe in order for this algorithm to work, we'll have to use more assumptions, because right now we're applying it to very raw data, and we're not incorporating any assumptions into the algorithm. So we're kind of going about it backwards. Usually when people design algorithms, they assume something about the data, and then they write an algorithm on that and test it on very simulative or synthetic data, and then they relax assumptions and see how it performs in real life. We're just applying it on real data right away, which I don't know how effective that'll be, but if it does work, that'll be pretty amazing, barring all the hyperparameter changes and what have you. So I will work on this for sure. We have 2 weeks, and then a 2-week break in between terms. Oh yeah, so that'll happen, and I'll be in communication with you guys through Slack. Two announcements. The first announcement is that the Theta Tau fraternity is planning that volleyball fundraiser, and I'm representing Drexel AI as well as another club, and we were asked to pick different local charities that we would like to represent, and I found this West Philly Coalition for Neighborhood Schools. I think it's a good thing to. I think they want to do like local charities for the fundraiser that are like in education. So I kind of like this, and I might suggest that to them in our meeting tomorrow. The second announcement is that my company Moberg, the boss, he really wants to form some data share agreement between his company and Drexel AI, which would give members access to the data set that we have, which is kind of amazing. We have really high physiological data, high resolution physiological data. For instance, like you could look at some of these patients here, and this is in a singular patient file. you have all of these modalities. You know, you have different things from EEG, then you have, you know, heart rate, diastolic, systolic blood pressure. And there's just, no, I'm not running the Docker container anymore, but we're working on a way so that people can actually access that just by being associated with Drexel AI, which would be pretty cool. There's a lot of good projects you can do. I submitted a paper to an IEEE conference a couple of weeks ago that deals with predicting events, you know, 30 minutes in the future using an array of features. And I feel like we could do something similar with more data, but that is to come. Yeah, so today's be short, but that's okay.
So wait, the data that your boss is willing to give us, that's for like any research projects that Drexel AI does as a group, or just like for the members for their own individual research stuff?
It would be for like Drexel. It'd be it wouldn't. Yeah, that's a good question. I don't know whether how guided it could be. I'd assume that he'd want it to be used toward. The idea is that the data is used toward his grant, so it'd probably be projects that I talk to him about, along with an IBM expert we work with. Sorry, an AI expert we work with from IBM, and we talk about projects, and then we'd do them as like a club. I don't know necessarily we'd be able to give, because the data the data that he's giving us isn't open source. It's from a clinical trial, so I can't. It'd be pretty dangerous to give it out and like anybody use it for other projects that aren't related to the goal of the grant that we have the data under. So, you know, it's something that we have to figure out from like an administrative point of view.
Cool. Okay.
Yeah, but it'd be really cool because you have, you know, it's called multi-modality monitoring data, which is completely time synchronized, and we're working on incorporating other data besides temporal data like images. We're working on incorporating images. I'm actually writing a grant with him to look at genomics as it relates to physiological data. I think that'd be pretty cool. So a lot of opportunities in connection with Moberg through Drexel AI. So I'm looking forward to that. Cool. For the paper, I know we want it to be done by the end of the term. That may or may not happen. What probably will happen is we'll get where we get with results and the paper, and I'll just post it on archive, and then we can always come back to it. There are papers that we've been working on that I'd like to come back to that we've posted on archive. For instance, right, we did this you know, protein structure project last term that I'd like to come back to, because I think that we can do better than what we did. And then there were some projects such as, you know, this looking at like LSTM and stock market prediction. Like this one was by Yit, but the code's on the Drexel AI GitHub. This was a univariate prediction, but I'd like to incorporate. Not too often do I see like a lot of. Not too often do I see like high resolution univariate, high resolution data from the LSTM incorporated with an array of multivariate factors. I don't know, it'd be cool to discover some, maybe not as they relate, maybe not in the scope of like stock market predictions, but it'd be cool to do it in like other sorts of modalities. Like if we had that data from Moberg, we could look at, you know, other factors besides just predicting EEG. From EEG, you could use other factors like other modalities or other things about the patient. I don't know. Yeah, cool. And then as always, project ideas are open for next term. I don't know. I don't have one in mind right now. But if someone has an idea, we can start talking about that as soon as possible for next term. This is our second to last meeting. Next week is our last meeting. That is week 10. And then we'll really try to wrap things up with a paper, and then I'll see about posting it to archive with what we have so far. And then we can always revisit it. Osamu brought up a good point for next term. We should focus on something that's a little more easier to reach for newcomers to the field because it's fall term. So I'm thinking about different projects that are not necessarily advanced, but will get people interested.
There's the one with like the race car track, right?
Yeah, I mean that'll be a project, but I'd like to do a paper or some sort, something that's, because that one's associated with a club. I'd like Drexel AI to have their own project they work on, because I don't think that everyone who's active will be interested in the race car one. And we might even do something, we could even do something with the data they collect from the race car that kind of intersects with that competition, so that we're not like doing two projects. We're not doing two separate projects. We're doing two projects that overlap. And you'd be surprised at how much working on overlapping projects saves you with time. The reason why I can do like an array of different things is because most of the things just overlap with each other. So I'm kind of cheating. They're not different things, they're the same things. Cool. All right. Yeah, if you have any questions, I'll be around, but that's all I have.
I have a couple questions.
Okay.
So can you explain like the volleyball thing again? Is it like we play for a charity or something?
You can play if you like. I mean, you don't have to play. We're still fleshing out the ideas, but it looks like everyone who wants to play from a club can come. Everyone who wants to play from the professional academic clubs. So that includes Drexel. We're a professional academic club. And then other clubs like the Drexel Biomedical Undergraduate Association, Theta Tau, SWE, Society, was it SWIC or, oh no, the woman in computing and informatics. Yeah, that one. WIC. Yeah, informatics and computing. Oh goodness, I'm messing that up. Yeah, they could all come out and play. The idea is for them to get donors, and then I think all of the money would go towards a charity, and then some portion of it would go to the club for fundraising.
I'll try my best. That's all I
Yeah, I'm not good at volleyball either, man.
Okay, and the other thing, so for the paper, right, I saw that it's some text was in blue and some text was in red.
Yeah, you
So
want to explain that? Sorry.
Yeah.
So black is everything that was before last week's meeting. Blue is everything I wrote in between last week's meeting and this week's meeting. Purple is corrections I made to other people's work. And then red is things we still need to add.
Got it.
Yeah, I will make everything blue besides the things in red later today. And then everything I add in this week will be blue. And then you can pick a color for things you add this week. You can pick green or something, I don't know. It's just a way for bookkeeping for who does what and who changes what and stuff like that.
And do we all need to pick a different color, or should we just?
I mean, you can all pick a different color, right? It's been like me and a couple people who are contributing right now, so we pick like 2 or 3 colors. So it hasn't been a big deal.
I mean, do we need to pick a color or not?
You don't have to. It's just something I do.
Okay.
Cool. You good?
Yep.
All right. Cool. I'll see you guys next week.
See ya.
Okay.
ya.
Bye.
I